All right, hi everyone, my name is Leo. I work on powdr, which is primarily an SDK for ZK VMs. And with that, we've built powdrVM, which is a RISC-V based ZK VM. But there's a lot more interesting things happening in the powdr SDKs. So the front end is flexible, that it can plug in different instruction set architectures, RISC-V, WASM, different things. You can also plug in different backends. Right now, there's like Halo 2, Plunky 3, and Stew. But the main thing I'm going to talk about today is one of the compiler techniques we have in the middle of the whole workflow, which is automatic synthesis of precompiles. And this happens basically before going to the ZK proof. So this is a technical talk. So it would be great if everyone is already deeply familiar with internals of ZK VMs.
Yes. Give me 5 seconds.
Yeah, so we first wrote about this technique in a blog post. If you want to read more in text form, it's there. But this, I think, was published last year. I actually don't remember. So there's probably more information, like more updated information in this talk, even though you'll find more information in general in the blog post. So the main topic here is precompiles or coprocessors or acceleration circuits or whichever name people give to it. So in ZK VMs, it's really important to have this idea of precompiles, which is circuits that you build by hand to replace computation that's expensive when you come from software. So if you have a Rust program that uses the tiny Ketchak library, it's a software library that computes Ketchak, that's going to use a lot of CPU cycles, a lot of RISC-V or WASM, whatever cycles to compute Ketchak. And if you want, and that's going to dominate the cost of your proof. So if you want to make that faster, you'd write a manual circuit that computes Ketchak with hopefully fewer resources than the CPU, like your VM, would take to compute Ketchak in the software form, which consists of a bunch of generic instructions. And if you take Ethereum, for example, there's a lot of different things you want to accelerate to make it even possible to prove like Ethereum blocks, for example, in reasonable time. And these would be, for example, Ketchak, ECDSA, SHA, and BN254 operations, because these would be very, very expensive if you compute them just in software and you let the VM take care of them. So this is, for example, what the beginning of the software Ketchak permutation looks like in RISC-V. So there's a lot of generic instructions. There's like adds, ends, XOR, shifts. The whole thing's going to be dominated by XOR and shifts. And this is only the beginning. There's actually almost 700 instructions to compute Ketchak. So it's a lot of code to do this computation. So you see there's a label up there, and this whole block is going to end in a branching instruction, and this is what we call a basic block. So you have a linear path all the way to the end, and at the end, you can also just continue from there, but you have like somewhere where you want to stop. And when you have a precompile, what you want to do is basically replace this whole thing here by one instruction. And what this one instruction is going to do is all of that. Not in the same way, not using the same amount of resources, but the result's going to be the same. So if before that block your memory had a certain content, and after that block you want address 12 to have the resultant Ketchak, this should do exactly the same thing. And what this instruction is going to do is it's going to use this newly constructed chip or circuit, air, whatever you want to call it, that knows how to compute Ketchak without using any of the XOR and add instructions that are generic to the VM. So this is quite efficient since, for example, these are very arbitrary numbers taking into account different current RISC-V ZK VMs. We're trading about 700 instructions, which is the amount of instructions we have sequentially to compute Ketchak, times 150 cells. This is like the amount of data you need at the same time. So for example, registers, memory locations, and so on, which we call this is the width of the CPU chip or the sum of instruction circuits, depending if it's a no CPU architecture. So you're trading that by a large chip. Now we have 1,000 columns or more in this new era, but we have very few rows, and we can basically compress all this generic computation into this amount of specific computation. And this will give us a lot of benefits, improve time and recursion and so on later on. So in the wild, you usually see 5x, 10x or more, depending on the case, speed up improving time for ZK VMs. And this makes precompiles essential for complex programs in ZK VMs, because ZK VMs, they can be very expensive if you're just doing generic computation, but for computationally heavy things like catch-up, ECDSA, and so on. So Ethereum blocks would be very complicated to prove if we didn't have these precompiles nowadays. This is what the Plonky 3 catch-up specific circuit looks like. This is only a part of it. There's hundreds of lines more of code. It's a lot of code. It's not super easy to read. And yeah, it was handwritten, so a couple humans probably wrote that. And the reason why I showed the Plonky 3 catch-up is because it's used by a lot of different ZK VMs. So a lot of different ZK VMs nowadays use Plonky 3, and they either use that circuit directly or an adaptation of that circuit. So this includes, for example, SP1, powdrVM, OpenVM, and probably others. And yeah, that's why I showed the catch-up one. But what if we end up with the workflow, which is common, that you have a complex guess program. It's not catch-up, it's something else. It's another hash function. It's MPT, it's something else. And you profile it in the ZK VM, and you notice something else dominating the cost of the proof. And now you want to optimize that. And then you do it again, and then you do it again. And then other companies do the same thing. And then in the end, we end up with tens, hundreds of thousands of these handwritten massive circuits that are very complicated to read and very complicated to write. So the main consequences here is that we're going to end up with a crazy amount of engineering effort that's not scalable. Everyone is doing a specific thing that, sure, other people can use it, but if the use case is different, then you're going to have to write a different precompile for that use case. And the second thing is they're going to be full of bugs. Enter auto precompiles. So why should engineers be doing this by hand if we can do it automatically? Well, the obvious answer is that you can't until this. So auto precompiles is an optimizer, an optimization feature that we wrote that basically does that. And it's fully automated. There's no human inputs. It's agnostic to the ISA. It only needs very little information about the ISA. Doesn't matter if it's RISC-V, WASM, whatever. It only needs to know what branching instructions are. And the encoding of the program needs to be a normal binary encoding. Not that it can't be done otherwise. It's just the easiest to integrate. And the performance is already comparable to manually written precompiles. So there's this expectation that manually written things will always be faster than the compiler can generate, but with time we've seen that this is not always the case. At some point you can't fool the compiler anymore, you can't be better than the compiler, and the expectation is that you can reach that at some point. On the security side, we're hoping that by having this one central way of automatically generating the circuits, that once this is audited, formally verified, and so on, this security basically scales to all the circuits that it creates, and you don't have to individually audit 1,000 precompiles that people have written all over the world. And the last thing, which is maybe one of the most important ones, it makes it more suitable for form verification. You can compile these automatic circuits in a certain specific way that if you write a toolchain once, that leads to having some form verification results, you can reuse it the same, like it basically scales to all the precompiles that you create other than instead of just writing them by hand and then trying to verify one by one. And in the first implementation we did for powdrVM, we saw 3x reduction in witness cells, and witness cells usually translates directly to proof time. What it doesn't translate necessarily into is when you do recursion, which is often the case if you have big proofs. You have this proof time for a lot of different what we call segments or chunks, and then you have this recursion tree that compresses like 100 different segments into a single proof. And we couldn't run this experiment end-to-end on powdrVM because we didn't have recursion. So we started integrating with VMs that do. And this also shows that this type of optimizations, they are actually applicable to any similar ZK VM, not only to powdrVM, as an optimization module. So you can take just that module and integrate it into different ZK VMs and still get very good results. So this was an experiment we ran with OpenVM. So basically using OpenVM's front-end ISA, then going to Powdr for optimizations, then going back to OpenVM for proofs. And what we see here is that in this experiment, we had 25,000 catch-up runs. The software version, there's no acceleration, it's just that massive block of code I showed earlier, leads to 49 segments. And a segment is basically when you have enough instructions that you're proving, usually about like 1 million instructions, that you're not going to be able to make a proof anymore. Or it's going to take too long, it's going to take too much RAM. So you stop at that point, you say, okay, this is enough for one proof, and you start again from scratch after that. And then in the end, you end up with a bunch of these, each proof proving basically 1 million or so instructions. And in the software version, we end up with 49 segments. And in the manual precompile, 4 segments. And the auto precompile version using this module end up with 9 segments. And yeah, the proof time itself is arbitrary. It doesn't really matter what the number is. So these are the things we care about. The first thing is, what is the improvement versus the software version? Because that's the reference, right? So the manual precompile version is able to accelerate this example by 11 times. And this includes these like initial proofs as well as the whole recursion tree to compress all these proofs into a single proof. The automatic one is almost 3.5 times. So this actually matches quite well and is actually better than this because it's a bigger number. And includes recursion, which is actually one of the bottlenecks of this approach. And the other number we're interested is when you take the manual precompile as a reference, because that's the fastest we have right now. And if you see here, it's almost only 3x worse than the manual one, which I think is really good results already because that's the fastest way we have to represent catch-up in ZK VMs right now, except maybe for Binius, in the RISC-V ones. So yeah, this is, so it's actually kind of in the middle. So like it's almost the same factor versus software and the manual one. So this is actually really, really encouraging results because of the benefits you get. Like it's 3x lower, but you don't have to write a single line of code. You potentially get better security guarantees, form verification, and so on. So for some cases, you might still be interested in writing a manual one to get the extra 3x on it. But if you think that you can get 2x, or I mean, this is going to improve, of course, but even if you have a 2x overhead by using the automatic version, that's already very powerful versus having to manually write a bunch of precompiles. Okay, how does it actually work? So what's happening behind this feature? So the basic idea is actually pretty simple. So in a ZK VM, each instruction is going to lead to a different set of constraints. It will depend on the architecture, if it's a monolithic CPU or no CPU, but we can use the monolithic one for now, which is you have a CPU has a bunch of registers, and these registers are used to compute the result of different instructions, adds, shifts, XORs, and so on. So every time you call instruction, you add a row to a table that represents the entire CPU with all the registers and so on. So every row is one unit of time. And all the constraints that ensure that these instructions are computed correctly, they have to be active in every row. So what we do now, we collect all the circuits from all the instructions that in this massive block from Ketchak. We put all of them together in a massive circuit, super wide circuit, that is as wide as the combination of all the instructions that we started with. Then the very first step, it's a very small step, but it triggers a whole bunch of other stuff, is inline and instruction arguments. So if you think about an XOR, you have XOR of AB equals C. And it's a generic way to apply XOR, and that's what the VM needs. But if you're accelerating a single instruction in that block, you actually know what the arguments are. In this case would be the indices of the registers. So you'd say XOR of the specific registers 5 and 6 need to go to the register 7, for example, which in RISC-V they're numbered from 0 to 31. So when you know this, you know the source location of a lot of the computation. You can inline these things in the circuits, and then this inlining propagates a lot of different optimizations that we can make. And yeah, after doing this, you just optimize the whole thing, and you get good numbers. So this is just a quick visualization of what it works, of what it looks like. So you can think about one row as all the data you need for one instruction. So you're going to have some instruction flags and some instruction arguments that tell you where you are and what you're doing. The instruction columns, which represent the actual computation being verified in that instruction. And then what we call bus interaction columns, which is how you communicate with memory, with some of the registers and different machinery you have underneath. Yeah. So the first step, what I mentioned before, you take all these rows that would be needed with all these columns for that block that I showed earlier, and you just put them next to each other. So this is now one super wide circuit that does catch-up. And each row of this is going to do what that entire block of assembly was doing at the beginning. But yeah, as the comment says, at this point, we're committing to the same amount of data as a software version. There's no improvements here versus software. We just took this and we did this. But now we can start optimizing things. The first thing is you see that here we have the yellow data, which is the instruction flags, but now we know what they are. They're written in the block, so they just go away. So we know what they are, including immediates at compile time, so we just remove them, and they don't have to be here. The next thing is we can start optimizing the blue and green parts, because a lot of data is local, so we don't have to keep going to memory and back, which instructions generically need to do. So now we can say, okay, I'm writing to a location, and then I'm immediately reading from it again. I don't need this write and read. I can just merge these two things. And the same thing then, if you end up seeing that something is a constant, you can propagate that constant and start simplifying or even solving for a lot of constraints. I don't know if you can read this, but this is an example of a really small block coming from a RISC-V program coming from Rust. So this actually does nothing. But it's a good example because it's small, because catch-up would take us 2 days to go through. Yeah, so you don't have to read this. It's just a sequence of instructions. But what I wanted to show here is that when you look at the program, the arguments of the instruction are constants. It doesn't mean that it's all constant computation. These constants are like the IDs of the registers, memory addresses, and this kind of things. But this is what has to be generic, because when you call an add, all these things inside that circuit are generic. But here they're not. I'm computing an add for these parameters, for these arguments. And if we turn this block into like this text form, this is what it's doing. It's updating the stack pointer in RISC-V, putting 1024 in register 10. Then it's putting this R10 in this address here, R2 plus 12, which we don't know what it is because R2 is symbolic at the beginning. This should be X2. But then we read this, we just set this address to X10, R10, we load this address again, and then we update the PC at the end with something we have to jump. But if we actually look at one thing at a time, so we have R10 equals 1024, this can be inlined. We don't need R10 for this. And when we have this store, it's like, okay, we can't get rid of it because maybe it's going to be used later on, but we can remember at least that address R2 plus 12 has 1024. Then we see that R10 equals R2 plus 12. This can be inlined as well. And the reason for this is that this is a linear expression, and it doesn't cost more if you inline them. It gets more expensive if they're not linear, but this can be removed. Then we're loading from address R2 plus 12, which is literally what we just wrote. So this load can actually completely go away, and we know it's 1024. Now we have R10 equals R0 plus 2. R0 is actually always 0 in the RISC-V spec because of hardware. So we know this is actually 2. We can inline it, remove it completely. And in the end, even this expression actually simplifies to a constant. And we know that even the condition can be removed. Everything can be removed. We know exactly where the PC is going to go. So this is an example that is so simple that we actually don't have to go to the circuits to solve it. You could solve it in the assembly level because the compiler just did a really bad job here, which is not unusual with LVM. But that's kind of like just to show more or less the optimizations you're looking for. Is just that usually it wouldn't be that simple in the assembly level, but on the circuit level, you can actually propagate a lot of this knowledge. So this is actually what the circuit is going to look like later on. You're going to have a lot of buzz interactions, doing range checks, memory accesses, and so on, and a lot of insane constraints. And so these are like a list of the optimizations we're already doing. So inline and instruction arguments, removing redundant memory reads and writes. And because now the data is local to the block, so I don't have to all the time for every instruction go to memory, come from memory, which is very common in RISC-V because of the stack model it uses in RAM. And especially in RISC-V, this is, we actually get an upper bound for the amount of reads and writes for registers that a precompile is going to do. It's going to be maximum 64, 32 reads and 32 writes maximum, because there are 32 registers, and you only have to keep the first read and the last write. Everything in between can be completely inlined. And when we remove memory accesses, usually the memory arguments are built in a way that need a timestamp, and you have to range constrain the timestamp difference from the previous one to keep it increasing. So now we can remove a lot of constraints. You can remove range checks, you can remove a bunch of other things. The same thing with redundant buzz interactions on the PC, because before this, every instruction has to commit to knowing what the PC is, what the PC update has to be, and what instruction has to be in like the ROM contained in the program. Now we don't need any of that anymore because we know at compile time what the PC update is for each instruction. And in general, this is kind of like a black box, but probably the most important part of all, simplifying complex constraints. So we start inlining things, and then in the end you end up with weird looking, quadratic, cubic, whatever, high degree constraints that they're not organized in a way that's like A equals this, B equals this, and so on. This kind of like easy to solve in a diagonal way. So they can be complicated to solve, but you can actually partially solve for a lot of variables. And this basically allows you to remove a lot of different columns, which is actually likely the main bottleneck of these circuits, just like having lots of columns. Actually, we ran an experiment. If you remove all the constraints, we have a massive precompile, an automated one for Ketchuk, which has thousands of columns, thousands of constraints. If you remove all the constraints, give it 0 constraints, and just keep the columns, the proving cost is still 90% of the original. So the important thing here is really to remove data, remove columns. And the constraints are actually not super important to remove themselves, but optimizing the constraints allows us to remove columns, which is just data within the constraints. So for this, we have a custom solver that takes these constraints and tries to solve for variables. And Chris and Georg here are the ones working with it, so if you have questions about the solver, you should ask them, not me. Yeah, so these are, and then this is what we see in this small example. So when we first take all the chips and put them together in the single chip, this is what we see. It has 200 something columns, 200 something constraints, and 100 buzz interactions. And after all the optimizations from before, this is the numbers we get. So it's about like a 4-5x reduction on the size. And if we go back to the Ketchuk example, this is the numbers we get. So the initial chip has 20,000 columns, which is an insane number of columns for a chip. So for reference, the manually written Ketchuk has about 2.5 thousand columns, 3K. I think it's about between 2 and I think 2.4, 2.6 thousand columns. And yeah, so 20K is, you would have 10x worse performance basically. But with all the optimizations together, memory constraints, columns, and so on, we managed to reduce it to less than 5K, which puts us within a 2-3x ratio from the manually written one. And this really translates to proof time, both the basic proof time and the recursion one. This a lot more to recursion. And this is basically almost like, actually this is last now, but the last time I ran these numbers, it was very close. Like the numbers we see in practice, like the 3.2, slower than Ketchuk, was very close to how many extra columns this circuit has. So it translates very closely. And some more exciting optimizations coming that will hopefully get us a lot closer to the manual one. There's more compile time constraint solving coming soon. More memory, redundant memory detection for the stack, which in RISC-V is a lot. And heap is, I don't know how much you can actually optimize there, but stack should be considerable. Propagating linear expressions up to degree bound. So this is like a niche thing, but if you have a lot of constraints that are like linear or quadratic, usually in the proof systems that these ZK VMs use, they accept up to cubic constraints, for example. So if you're not using cubic constraints, you're kind of missing out, because you could inline some of these expressions to end up with cubic constraints and remove columns in the process. And air stacking is an even more complicated optimization, which is useful for when you have a lot of precompiles, because then recursion gets really expensive. And if you have a lot of precompiles that are very wide, but they don't use as many columns, as many rows, sorry, that would occupy a whole segment, you can actually take these two different precompiles and merge them, just put them on top of each other, because now they have the same width and more rows. As long as they fit, this is more efficient, and you just got rid of a bunch of columns. But this is probably the most complicated one. And the goal is to get the automatic Ketchuk precompile to be faster than the handwritten one. That's it. Thank you.
Can you train AI to be good at this?
Probably not.
Then my next question is like, where does this start to fail? Is it because of obviously training data, or because you actually need to instruct this whole algorithm of reduction?
For some of it, AI could do, but where AI is not going to succeed for a long time is simplifying the constraints.
Yeah.
It's just really bad at math, and this is, yeah, it's not going to be good at it.
And you're not going to ensure any kind of security, so I mean.
Yeah, I guess like with AI, you would have to have form verification as a requirement in a way. Like you have to prove that the generated chip does the same thing as the original one, right?
Sure.
So I think that requirement becomes a lot stronger in the AI case, instead of like heuristics and math solvers. Yeah. Sorry, behind you was first. Yeah.
Out of all the optimizations that you have on your list, are there some that are simply not possible on the LLVM, compiler before even getting here?
I mean, the circuits basically, because this doesn't exist there, right? So when you get from, I don't know, mstore in LLVM, when you get the assembly, it's just like literally an instruction, right? But when you get to a circuit, it's going to be implemented as a sequence of constraints, or like a set of constraints that have nothing to do with LLVM. And this is what actually is expensive in the end. So you can do high-level optimizations, which will have an impact, but some of them just won't exist until you get to this point. Yeah.
And the second question is, can you take this like to why would you stop at a block? Why wouldn't you precompile something much larger? Is there a limit, and the limit is what?
Yeah, that's a good question. So there's one idea that you could actually turn the whole program into precompiles. You take every single block in the whole program, and then your final program is just precompiles. And it's a pretty theoretical idea at this point. I actually tried it on an EVM, like on Wrath, basically. And you end up with like almost 5,000 precompiles. And I didn't even try to make a proof for it because, yeah, recursion will just get destroyed. I think for that, you would need a very strong air stacking at least. But also, like, I literally did for all of them, but that's also very clearly not a good technique because you want them to be at least somewhat expensive. Because if they're cheap enough, it's not useful to optimize them. You can just spend the instructions and it's fine. Yeah, so there must be like one thing we also do is just like some profiling guided optimization. So you just profile it first with some sampled inputs to see what the hot paths are and this kind of things, to see which basic blocks to optimize. Because if a block is never used, you could be paying for a lot more columns, even though you use like once or twice, it's not worth it. Sorry.
Yeah,
That was my question.
Oh.
Okay, cool.
If I remember right, the Ketchak circuit in Plonky 3, which I guess was like the handwritten reference, basically bit decomposes the
Yeah.
entire state. So
Yeah.
it's like 1600 state columns. Is
Yeah.
that also what you end up with?
No. I think that's specifically for Ketchak, I think that's why we can actually be more efficient at some point because we're not doing the bit decomposition, which ends up being pretty wasteful, right? It makes it easier to write the circuit.
Yeah.
So what Jim's referring to, so in the handwritten circuit that I showed here, it basically implements Ketchak by bit decomposing the whole state. So each column is a bit, which is pretty wasteful in terms of data. It makes it easier to write the circuit and the constraints become simpler. But as far as number of columns go, it's pretty wasteful. And in our case, we end up with the higher level instructions because like if a Ketchak does a shift in RISC-V, then it's going to use a shift chip. And the shift chip will probably not bit decompose it. It's probably going to use lookups.
I mean, shift is a bad example, I guess, right? Because if you shift bits, you can just multiply, copy them. There's no operation involved in the
Yeah.
decompose.
Yeah. Yeah, but like XOR, for example, in this case, I mean, in this case, it's going to use the bits, and then it's going to use one bit, one column for each bit. Whereas in our case, it's going to be turned to lookups, into byte range checks, and the lookup for the XOR result. So the XOR should be more efficient than in the handwritten one. But yeah, that's more like a coincidence. But I guess like this would be a common effect. Like when you write the manually written circuits, you can optimize for readability somewhat, or for the full optimization of the handwritten circuit, which then might make it even less readable. So I think that's also a good point. Sorry, Oliver, you had a question.
Yeah, just a quick question. Do you want to do the compiler also instruction set independent?
It is independent. So this is RISC-V because that's the ISA of the provers we ran with powdrVM and OpenVM, but it is actually fully agnostic. It only relies on, I mean, it's already actually implemented on the powdr implementation of RISC-V, which is not RISC-V, it's just an approximation. And same for OpenVM. It's implemented for the OpenVM internal ISA, which is like somewhat RISC-V, but it's already the internal ones, so it doesn't have to be RISC-V. And the only thing that it relies on is knowing what branching instructions are, which could also be automatically detected, but at this point it's just easier to know them because we know. Yeah, Jim. Sorry. No, it was your, yeah.
Yeah, so when we do actually these coprocessors in hardware, we sometimes reuse resources. So for example, if two coprocessors next to each other both need multiplier, you may actually just end up with one multiplier in hardware, but then two of them virtually share it for optimization. Can your optimization share resources so that you kind of end up with 1.5 coprocessors with appear like two coprocessors from the function perspective?
Yeah, you could. There's nothing that prevents it. At the first implementation, it depends on what the original chips are doing in the first place. So, and one example is, again, XOR.
Yeah,
so if you have two different precompiles that use XOR, they will both end up using the same lookup chip.
I see.
So that's already shared. But some other chips, they have some inline chip that they, like for example, I think there's like a less than small error that gets inlined every time it's used. So this would be different copies, but just because of the way the original chip for the instruction was written. But if the original chip uses like a common one via what's called the bus, then it will end up shared as well in the final precompile. But if it's inline, it's going to be inlined as well, but it's also something that could be further optimized later on.
So that's very intuitive for arithmetics. How about memories? Can you like share buses maybe, like, or have a notion of scratchpad to be shared?
Yeah, so the memory is the same memory as before. So the only thing we do with memory is remove all the redundant accesses, but the accesses that remain, they still use the same memory as before.
Got it.
Yeah.
Thanks.
All right.
Cool. Thank you.